So our first talk will be about the quantum register machine, efficient implementation of quantum recursive programs by Zhicheng Zhang. So take it away.
Okay. Hi, everyone. My name is Zhicheng, and today I'm going to talk about our recent work on quantum register machine, efficient implementation of quantum recursive programs. This work was done in collaboration with Mingsheng Ying. Let's start with why we need quantum programming. So suppose you are going to design a quantum algorithm, you can first write it as a high-level quantum program. And if you have a compiler that can compile this program into low-level quantum circuit, then it can be implemented on a quantum hardware. So in this process, there are two goals we hope to achieve. The first is we hope the high-level quantum programming languages allows you to have a convenient description of the quantum algorithms. And the second goal is the compilation process provides an efficient implementation of the program. So these two goals are actually related. Now for quantum recursion, we need two programming features. The first is the recursive procedure calls, which is widely used in the classical computing. It allows a static short program text to generate a dynamic long computation. There are a lot of examples of classical recursion. And the second programming feature is called quantum control flows, which is essentially a superposition of program execution. So it is often guarded by the quantum if statement, which is just a quantum version of the classical if then else statement. So here Q is a qubit, which is also known as an external quantum coin. If Q is in state kit 0, then we execute the program C0. And if Q is in kit 1, then we execute the program C1. Of course, Q is a qubit, so it can be in a quantum superposition state. In this case, we execute C0 and C1 in superposition. Another way to look at this Q statement is by writing its corresponding unitary, which is just a combination of two controlled unitary, where each UI corresponds to the semantics of program CI. Okay, so quantum recursion is just a combination of these two features. So if you want to implement quantum recursive programs, a good implementation should support these two features harmoniously, and a better implementation should be efficient. The interplay between these two features is actually intricate. At this point, you might ask why we need quantum recursion. So here is a motivating example. There is a subroutine widely used in quantum algorithm called quantum multiplexer, whose unitary can be expressed in this form, which is just a summation of many controlled unitaries conditioned on the first n control qubits. So a straightforward implementation of this unitary is just by a sequential product of these controlled UX. And it is easy to see that the time complexity of this implementation is proportional to the sum of all Tx, where each Tx is a time complexity for implementing this controlled UX. In comparison, actually, we can do better by some manual designed quantum circuit as shown in these two works, which achieves a parallel time complexity proportional to the maximum of Tx. So this maximum compared to this summation is an exponential improvement with respect to the parameter n. Now, a natural question is, can we design at high level and still obtain this efficiency automatically without the complicated manual design? The answer is yes. First, we can design a quantum recursive program as shown on the right-hand side, which is written in the language PLanQC'25 proposed in our previous work to describe this quantum multiplexer. So here, as you can see, the central procedure is PKX. And on the right is the procedure body defining this procedure. And we have this QIF statement going into two quantum branches. And each of these branches call the procedure P itself with different classical parameters. And so now you can see the interplay between the quantum control flows and recursive procedure calls. Then we can compile this program and load it into a quantum random access memory known as QRAM, which is just a quantum version of the classical RAM. And if you further have a machine that supports quantum control flows and recursive procedure calls, you can execute this program on this machine. And an important thing to note is these two quantum branches, they will be executed together in superposition. So that means the time complexity for implementing this QIF statement only depends on the longest quantum branch. So the induced overall time complexity will be proportional to the maximum of Tx, roughly speaking. So how can we achieve this? Now I will talk about the contributions of this work. So first we proposed an architecture called quantum register machine, which supports these two features at instruction level. So it has an instruction set called qins. And we proposed a comprehensive implementation process for quantum recursive program. Now suppose you have a program written in the high-level language RQC++. Now we can first compile it into the instructions in qins. Then we can perform a partial evaluation of quantum control flows in the compiled program to obtain this quantum control flow information, which will be loaded into the QRAN together with the compiled program. And this additional information will aid the execution of the compiled program on the quantum register machine. The above implementation is actually efficient that it even offers some bonus. It can allow automatic parallelization of certain quantum algorithms, including the example of quantum multiplexer. It automatically yields a parallel time complexity proportional to the maximum of Tx. Okay, great. Now let us get into the details. So for the architecture, like a classical CPU, a quantum register machine operates on quantum registers and executes a compiled program by fetching instructions from the QRAN, then decode and execute these instructions. So the storage components of the quantum register machine are just the registers and the memory. The registers include the user registers and several fixed system registers, and the memory is a QRAN, which is divided into several sections. So remember, we want this architecture to support quantum recursion, so it needs to handle the previously mentioned two features. So to handle the quantum control flows, inspired by the previous work by Yuan, Villani, and Carbon, with ideas borrowed from the classical reversible architectures, we put the program counter into a quantum register PC. So this program counter just points to the current instruction you are executing in the program section. Now, compared to existing works, the challenge here from the quantum recursion is how to automatically handle the synchronization problem, which will be explained later. Roughly speaking, the synchronization problem refers to when you, in the implementation of the QIF statement, it will generate two quantum branches, which will take different time to terminate. So here the time is measured by the number of instruction cycles to execute these two quantum branches. And if you want a single quantum register machine to execute these two quantum branches together in quantum superposition, you need to synchronize these two branches. Now, the recursion makes this picture more complicated because it introduces some non-determinism. So our solution is a partial evaluation of quantum control flows and generate a data structure called QIF table, which will be loaded into the QRAM and used in superposition during the execution. We also designed 3 system registers and corresponding mechanisms for this to be done. Now, to handle recursive procedure calls, we just allocate a call stack in the QRAN, like in the classical case. One important thing to note is everything in the quantum register machine can be in the quantum superposition state. That means all registers and the QRAN can be quantum entangled. For the instruction set qins, we designed 22 instructions. Most of them are inspired by the classical reversible instruction set architecture. But to handle quantum recursion, we need to introduce some novel instructions. So for example, these two are instructions to handle the quantum control flows. And we also need instructions to implement quantum unitary gates. And these 22 instructions are characterized into 3 types according to their format, for which we can design a decoding unitary to decode and execute these instructions. Great. Let's move on to the implementation part, starting from the compilation. So the compilation consists of 3 passes, including the high-level transformation, high-level to mid-level translation, and mid-level to low-level translation. So this process compiles a program written in high-level language RQC++ into the low-level language QINS. And the mid-level is just a simplified version of the QINS. Of course, the compilation process is independent of the program input and only depends on the program text. And this process is inspired by the compilation of classical reversible languages. Now, what's the target of these 3 passes? So for high-level transformation, we want to simplify the automatic uncomputation in later passes. Why uncomputation is needed? Because the high-level programming language RQC++ allows you to use classical variables to specify the control of the program. And operations on classical variables can be irreversible. But we hope to use a quantum unitary to implement this whole process. So we need to make these operations reversible by introducing some garbage data, which has to be properly uncomputed. Now, the second pass just translates the high-level statements to the low-level instruction. And the third pass majorly handles the memory allocation of classical and quantum variables. Now, here is an example of the quantum multiplexer program again. On the left-hand side is the program after high-level transformation with some new variables introduced to simplify the structures of the program. On the right-hand side is the high to mid-level translation of the procedure PKX, where we just translate each part, including like the initialization of classical parameters and disassignments of classical parameters and the quantum if statement, the procedure calls. We just translate each of these into these low-level instructions correspondingly. And here you can see there is a uncomputations, a piece of instruction for the uncomputation of the classical variables, and it is done at the end of the procedure body. Now we can talk about the partial evaluation. So remember, the target of our partial evaluation is to automatically handle the synchronization problem. So the following diagram shows how we synchronize different quantum branches. If 2 branches generated by a QIF statement has different number of instruction cycles to terminate, then we can let one of the branches to wait for the other for some number of instruction cycles. But the difficulty introduced by the recursion is the non-deterministic number of nested procedure calls. So our solution is we can partially evaluate the quantum control flows given a classical input, which specify the control of the program. But we don't need to know the quantum inputs. And we also set a practical time to check if the program terminates within this practical time. Since we allow the while loop and recursion, it might contain some decidable problem. So we need this practical time. Then we can generate a QIF table, which is a data structure recording the history of all quantum branching. The QIF table is just a graph where each black node in this graph represents an instantiation of the QIF statement, and white nodes are ancilla for reversible implementation of the QIF table. Each black node will store a counter W for the number of instruction cycles to wait at the current node. So during the execution, we will read information from the QIF table in superposition and know the number of instruction cycles need to wait at the current instruction cycle. And between these nodes, there are links representing the nesting or non-nesting relations between the instantiation of the QIF statements. And finally, for the execution, we'll load everything into the QRAN, including the compiled program and the QIF table. So just like the classical CPU, the quantum register machine just repeats doing the same operation at each instruction cycle, which is this unitary ucyc. And we will use information from the QIF table in superposition to know whether we need to wait at the current instruction cycle and how long we need to wait. And if we do not need to wait, we can execute. So we just fetch instructions from QRAN and then decode and execute it using the decoding unitary and unfetch because we need to make it reversible. And finally, we need to deal with the branching instructions. Great. So that's implementation, and it is actually efficient. And it even offers automatic parallelization of some quantum algorithms, including the quantum multiplexer. So here is the theorem for implementing the quantum multiplexer via the quantum register machine, which shows quantum circuit to implement this quantum multiplexer with circuit depth proportional to the maximum of Tx. And it is exponentially better than the straightforward implementation, although slightly worse than the manual design. But after all, it is automatic, and it will save the time for the quantum programmer to design this quantum algorithm. Okay, so the take-home message is simple. Quantum recursive programming can be win-win. It can achieve both goals of convenient description and efficient implementation. So you can try it in the design of quantum algorithms and protocols. For the future topics of this work, first, our framework is theoretical. So an immediate question is whether we can have a software implementation of this framework. And of course, we can extend the features of this framework, and there are many optimization opportunities in this framework from the compilation to the execution. And the last topic is whether we can obtain more quantum algorithmic speed up from the perspective of programming languages. That's all of my talk. Thanks for attending.
Okay, is Zhicheng online for questions? Okay, great. So I have time for a few questions from the audience. I'm happy to start us off. So you're probably aware of various papers early by Badescu and Panengaden, and more recently Charles Yuan wrote a little bit about this, about sort of the limits of control flow in quantum computation. Can you talk a little bit about how you are getting around these limitations that these various papers have identified?
You mean like what difficulties in these above papers?
Yeah, so these recognize that there are difficulties in having like an unbounded while loop or recursion in a quantum program, and I'm wondering if there are like limitations in both the like high-level language and in the lower-level language you've introduced that kind of make it these compilable to circuits.
I see. So the high-level language, so it's in our previous work. So compared to previous existing work, our high-level language allows you to do the procedure calls with arbitrary classical parameters, which is not supported in the previous works. And about the architecture, we also support the quantum recursion at the instruction level. So, so the previous work only supports the quantum control flows at the instruction level. That's the major difference.
Okay.
Hi. So most hardware today doesn't have QRAM. So I'm wondering, what are the actual assumptions that you're making on the quantum memory in order to implement this? What's the interface to the memory?
Okay. So our architecture requires QRAM, which is, for simplicity, we assume it is a quantum read and quantum write QRAM. And for the example that we have for the quantum multiplexer, we actually implement this QRAM. as a quantum circuit. So the results about the implementation of the quantum multiplexer is with respect to the quantum circuit implementation. But if you have the QRAN, then what you need is actually like the standard quantum read and quantum write access to this QRAN. So you just specified an address into the QRAN, then the QRAN will return the data specified by this address in superposition.
All right, let's thank our speaker again.
Thank you for all these questions.